The process for drawing Lewis structures for entire molecules is simply a little more complex, and it comes down to using what we call the octet rule. If you look up here, when we're done with this particular Lewis structure, you'll notice that chlorine actually has a full valence shell now because it stole that electron from sodium. So it now has 8 electrons around it. Since chlorine is a nonmetal, that's sort of ultimately its quest, to try to bond with something and steal electrons so that it can fill that last energy level. Sodium, on the other hand, is losing that electron since it has sort of 1 extra electron, and then it drops back and it has 8 valence electrons below that once that one's gone. But I don't really see those 8 valence electrons. All I see is this one that's right here. So when we're done with our structure, we use what's called the rule of 8. And basically it takes a look at the fact is we're going to count electrons all the way around non-metals specifically. And the octet rule for Lewis structures is that all non-metals will have 8 electrons, 4 pairs around them in their molecular structure. Metals, on the other hand, will have 2 or 4 or potentially 6, but they can really have any number. It's really the non-metals that we're going to kind of use this rule of 8 for, because non-metals tend to try to steal electrons and metals try to get rid of them. So what we're going to try to do here is to look at, in general, how this process might work with an ionic compound. So if I'm looking at building a compound between sodium and oxygen, sodium has a charge of +1 and oxygen has a charge of -2. So to match those two up, we're actually going to end up bonding 2 sodiums with 1 oxygen in order to make this happen. Again, following those same ionic compound rules for neutral compounds. So going back to what we had before, I have sodium with its 1 valence electron. So this is how its electron dot diagram would look. Oxygen from the periodic table would have 6 valence electrons. So it would look like this. Again, bouncing around each of those structures that I have there. And now there's 4, and I'll put the 5th one there, and I'll put the 6th one there. So oxygen has 2 pairs and 2 singles in this particular process. So again, the formula is Na2O. So what we're going to do at this particular point is take this and drag it over here, and you can see that if sodium donates its 1 electron right there, it can form a bond with 2 electrons between sodium and oxygen and create an extra electron for oxygen. Well, why does oxygen require 2 sodium atoms? Well, the other sodium atom looks exactly the same way, and oxygen is still missing 1 valence electron. So by bonding with a second sodium atom, I end up now with my structure that might look something like this. Now, to see whether or not this structure is correct, what we're going to do is use the rule of 8, which says all nonmetals need 8 electrons around it. So here again, here's oxygen. I can count 2, 4, 6, and 8. It has 8 electrons around it, so it's set. Sodium is a metal, so it does not need to follow the rule of 8 because it's actually losing these electrons anyway. So it doesn't really matter. And so this is how we're going to build a structure and recognize how these molecules are actually put together. So what I'm going to do now is kind of go through really what is the 4-step process for taking any molecule and determining the steps for determining a Lewis structure for a molecule. And I'll bounce back and forth with this and an example. So rule number 1 is basically we want to add up the total number of valence electrons that are available in the molecule. So bouncing to an example, let's say we're going to take CCl4, so 1 carbon and 4 chlorines, and bond them together. So my first rule says add up the number of valence electrons in the molecule. So looking at the periodic table, carbon has a total of 4 electrons. So carbon has 4 valence electrons. Okay? Now chlorine from the periodic table has 7 valence electrons, but there are 4 chlorines. So 7 times 4 gives me 28 valence electrons from chlorine. So now the total number of dots that will be in this particular molecule is going to be 32. So there are 32 valence electrons in this particular process. And so that's how many dots we're going to have around that particular structure. So now going back, step number 2. All right, what we're going to do in step number 2 is determine what we call the central element, what everything's bonded to. Now, in general, these are the rules. It's never hydrogen. And the reason it's never hydrogen is only has 1 electron that's in the first energy level. And if you remember that it only needs 1 more electron, because the maximum number of electrons you can put in the first energy level is 2. So hydrogen doesn't have many places to bond because it only needs to either lose or gain 1 electron. So hydrogen is never the central element. Central element rule number 2, it's almost never oxygen. Sort of a rule number 3, if there's a carbon atom, it's probably the central element. And so those are the 3 things that are designed to help you out a little bit in terms of describing those structures. So if I come back here, I have carbon and chlorine. The other thing is basically this, how we write these things now, is usually tells you a little bit about the structure. So number 1 for my rule, this has carbon in it, so that's probably the central element. The other way to look at this is when I write this, this basically says I have 1 carbon and attached to it are 4 chlorines. And so that means that the carbon is going to be my central element. So what I'm going to do now is I'm going to draw what we're going to call our skeleton sort of structure for this. I'm going to place carbon at the center, and remember I have 1, 2, 3, 4 locations that I could bond atoms to it. And I actually have 4 chlorines. So basically, where we were putting those valence electrons before, I'm going to place a chlorine atom there. I'm going to place a chlorine atom there. I'm going to place a chlorine atom in that spot. And I'm going to place a chlorine atom in that spot. Each of those 4 locations. Slide that in just a little bit more. Okay, so now I have 32 electrons that we're going to put in place. And so coming back to my rules, I've got my central element, and next I've created my skeleton structure, and I'm going to bond the atoms with what we're going to call single bonds. And from earlier, remember that single bonds are 2 electrons. And so frequently, instead of seeing the 2 dots, what you'll see instead is just a line that connects the 2 of those atoms in that particular spot. And so this represents a single bond composed of 2 electrons between the structure. So I'm going to have a bond there. I'm going to have a bond here. I'm going to have a bond here. And I'm going to have a bond there. So there's my 4 bonds. So that represents 8 electrons in this particular structure. And so there's my skeleton, and I've bonded them together with single bonds between the 2 of them. Okay, so I created my skeleton structure, and I bonded the atoms with single bonds. Now, what we're going to do is we're going to look for the octet rule for all nonmetals. And what I mean by that is, so far I have 2, 4, 6, and 8 electrons on there in those 4 bonds, but I have 32 valence electrons that need to go on there. So what we're now going to do is start bouncing around this molecule, adding more valence electrons to the things that still need 8 electrons. So if I look at carbon, carbon is a nonmetal, so it needs to follow the rule of 8, or the octet rule, and so I'm going to count 2, 4, 6, and 8 electrons around carbon. It's good to go. However, if I look at the chlorine, this chlorine currently only has 2 electrons, this 1 bond around it, and that's repeated in those 4 spots. So what I'm going to do is start bouncing around the molecule, putting pairs on there to make that look easier. Okay? To make my life a little bit easier, I'm going to use little smiley faces to represent my electrons, since they're easy to draw with my software here. Okay? So what I'm going to now do to represent those electrons, there's 2, 4, 6, 8. There is 9 and 10. There is 11 and 12. I'm just putting them on in pairs, 13 and 14, 15 and 16. And now I'm going to come back around. Does this still need more electrons? Sure does, because it's only got 2, 4 now. So I'm at 16. There's 17, 18, 19, 20, 21, 22, 23, 24. Does this one still need more? Yep. 25, 26, 27, 28, 29, 30, 31, and 32. And now I'm out of valence electrons. I only had 32 to start with. And so now what we're going to do is go back through now that all of the valence electrons are actually on there, and we're going to count valence electrons for all of them. So this chlorine now has 2, 4, 6, and 8. This chlorine has 2, 4, 6, and 8. And so what you can see is all of the atoms that are in there have 8 electrons around them. And so we're going to say, based on our rule of 8, that this would be the structure for carbon tetrachloride CCl4. Let's do one more example, and so let's take a look at carbon disulfide. And so, again, going back to my rules here, rule number 1, we're going to add up the total number of valence electrons in the molecule. So, again, if I have carbon off the periodic table has 4 valence electrons. Sulfur has a total of 6, but there are 2 sulfurs in this molecule, so now I have 12 total valence electrons for sulfur. So the total number of valence electrons this time is only 16. Last time I had 32. So that's our first task. Second task is we're going to determine the central element. It's not hydrogen, it's not oxygen, and if there's a carbon, it's usually the central element. So here again, I got carbon, and again, this says I have 1 carbon and 2 sulfur attached to it. So I'm going to take my carbon, place it in the center, and then I can put the sulfurs, the 2 sulfurs, anywhere I want to. For ease and for space, I'm just going to put them on opposite sides so that I can draw their structures that are there. Okay. Next thing I'm going to do is I'm going to create my skeleton structure and bond the atoms with a single bond. So I'm going to bounce back here, grab my little bond symbol, and I'm going to bond the carbon with the sulfur like that. Okay? Now, that gives me 4 electrons, so I still have 12 more electrons to stick on my diagram. And so what we're going to do is we're going to start using that octet rule for all nonmetals. Well, both carbon and sulfur are nonmetals, so this means that I need 8 electrons around all of these. So again, I'm just going to start randomly putting them some places. Okay, again, I'll go ahead and use smiley faces to represent my valence electrons. So there's 2, 4. Sulfur needs some more, so there's 5, 6. Carbon needs some more, 7, 8. Sulfur needs some more, 9, 10. I'm just putting them on in pairs and working my array around. Okay, so now I can come on back around since I made it through it. Sulfur still needs more, so 2, 4, 6, 8, 10. I got 10 on there, so there's 11, 12. Carbon still needs more because it's only got 2, 4, 6. So there we go, 1, 2. Okay, and let's see how many electrons I have now. So 2, 4, 6, 8, 10, 12, 14. I've got 1 more pair of electrons that I can stick over here and stick those right there. Okay, so there's my pairs of electrons that go on that particular structure. So now we're going to use the rule of 8. Is my structure correct? Well, it is if all of my nonmetals have 8 electrons around it. So if I look at carbon here, you can see I have 2 bonded pairs, so there's 4, 6, and 8. Remember the bonds are 2, so 2, 4, 6, 8. So carbon's happy, it's good to go, all right? Sulfur, however, has 2, 4, and 6, and 2, 4, and 6. And so it does not match the rule of 8. But I don't have any more electrons to stick on there. All right, so what we're going to do next is, if I can't make the structure actually work with single pairs, then we're going to use what are called double or triple bonds. if the structure doesn't work with single bonds. And so when I come back here, here's a situation where I can't make this work with single bonds. I don't have enough electrons. And so what's going to happen is we're going to take the 2 electrons around an atom that already has 8 and move them in between the 2 atoms to create what we're going to call a double bond. So right here I have 2 electrons that aren't really doing anything in terms of carbon. They're hanging out there. And so what I'm going to do is shift them over here. So what I'm going to do is I'm going to replace those 2 electrons with another bond. Okay. And so there's my 2 electrons that were sitting there. And what's going to happen is I'm going to slide them right over here. And now I've created a double bond between sulfur and carbon. Now carbon still has its 8 electrons because there's 2, 4, 6, and the 2 lone ones that are there for 8. But now I've satisfied this sulfur's rule of 8 for 2 and 4 and 6 and 8. And so those are good to go. So now basically what I need to do is do the same thing on the other side. I need to steal these 2 electrons from carbon that aren't doing anything. Remember, it already had 8, and I'm going to just shift it over and form a double bond. So once again, I'm going to pull those 2. I'm going to replace those 2 with a bond, and I will simply draw my bond right there between the 2 of them. And so now I have satisfied the carbons with double bonded on both sides, and I've satisfied the sulfurs on each side by nailing those down as well. So if double bonds still don't work, you can try a triple bond between atoms, and that's as far as it goes. There aren't really any quadruple bonds or beyond in that particular process. That completes this lesson on drawing Lewis diagrams for molecules.